Gostaria de agradecer imensamente ao meu grande amigo Greg, que nos proporcionou a nossa apresentação hoje do Dr. Daniel Fowler. Daniel, é com você.
My topic today is cybersecurity engineering in connected and automated mobility. It's about building cyber resilience in transportation systems. So I'm Dr. Daniel Fowler. I'm a research fellow at WMG, which is at the University of Warwick in the UK. I work within the Secure Cyber Systems Research Group. WMG was founded 41 years ago, focusing on industry and management and manufacturing technology. We are an applied engineering and manufacturing research facility. We provide postgraduate teaching, and we're located in several buildings on the Warwick campus near the city of Coventry in central England. Coventry and central England is the historical heart of the UK's vehicle manufacturing industry, with vehicles such as Jaguar Land Rover, Aston Martin in the local area. We link academic research with business and educate the next generation of engineers and industry managers. The Secure Cyber Systems Research Group is a group of 25 plus researchers with projects such as Internet of Things, communication systems, vehicles, space systems, cyber policy, trust, identity, privacy and security projects, and digital forensics. We work with many universities, companies and organizations. We deliver fundamental research through collaborative research and development and contracted research. Why cybersecurity engineering in connected and automated mobility? Well, connected and autonomous vehicles, CAVs, are here. Automated mobility is being deployed. At the university, we're working on autonomous very light rail for the Coventry city. Electric vehicles are here. Jaguar produced many electric cars in our locality. And vehicles are now connected and very, very much driven by software. So how can automotive engineering reduce the risks from cyber attacks? First, a bit of background. All vehicles use interconnected computers. Multiple computers are very common within vehicles. This BMW has 30 electronic control units. They're computers, known as ECUs. Everything in a vehicle has a software or computer element. Engine, gears, powertrain, airbags and safety, infotainment systems and climate control. Even the cabins, seats, doors and switches are all computer controlled, and they're all interconnected. The networks within vehicles are fairly complex. And today, vehicles are all produced with connections to the outside world. What does connectivity mean? It means hacking. Automotive hacking is aimed at vehicle systems. Hacking is a part of engineering. This UK Autodrive project took standard vehicles and added sensors onto them to make them autonomous. But hacking has revealed security issues. The most famous was back in 2015, when American hackers took control of a vehicle, an unmodified vehicle, remotely over a cellular connection. They proved in a real-world scenario that vehicles can be compromised. What are the threat motivations for attacking transportation systems? Whereas the most common is financial gain, vehicle theft. Vehicles are valuable, not only as a whole vehicle, but their parts and the goods they carry. In the future, vehicles will be producing personalized data sets. The engineering within a vehicle is of interest for IP theft. Transportation users of transportation systems may want to gain free rides. Passengers will be using their own car details stored on onboard systems, or using their payment details to access transportation. Those card details are valuable. As well as the financial motives for hacking, other hacking motives exist, include vandalism. People hack things just because they can. Then there's nation-state actors and terrorists who may want to cause chaos, block roads, crash vehicles, or use vehicles as terrorist weapons. Eavesdropping on the passengers within vehicles could also be a reason, and it has been done before. And attackers may want to target VIPs and wealthy individuals who travel in transportation and luxury cars. So there are plenty of threat motivations for attacking transportation systems. And attacks are happening as we speak. The most famous is probably the simple relay attack, where the keyless fob entries to vehicles are compromised to steal vehicles. The thieves will use communications equipment to relay the signals from key fobs to an accomplice that stands by a vehicle. They can then gain access to the vehicle and drive it away. But hacking doesn't just necessarily need to be about theft. Dieselgate emission scandal, in which cars were fitted with software that enabled them to falsely report emissions during testing, is another example of hacking within the automotive transportation system. This corporate hacking was because of device defeat software that overcame the emissions testing regulations. And what about a vehicle virus? Ransomware is now very common. What if you got into your car and you couldn't start it because of a ransomware attack on your vehicle? Ransomware is for financial gain. The WannaCry ransomware attack by June 2017 had totaled $130,000 in payments. As Elon Musk says, one of the biggest risks for autonomous vehicles is someone achieving a fleet-wide hack. And ransomware has already affected transportation systems. The San Francisco Transit, the payment system, was taken offline from a ransomware attack. In Alaska, flights had to be cancelled after an aircraft maintenance system was taken down. How do we hack transportation? We use similar methods against other systems. So we compromise the confidentiality, integrity, and availability of the systems. We can use traditional hacking, traditional pen testing, vulnerability assessment, and fuzzing techniques. Malicious code can be embedded into the systems. And we can spoof the signals and the data that's within the computer systems in the vehicle, or perform denial of service attacks. So these are ways that we're very familiar with attacking any type of computer-based system. And vehicles present a huge attack surface for the threat actors that may wish to attack transportation. So we have internet, cloud, and data communications. This can be via Wi-Fi, 4G, 5G, and manufacturer services. Many manufacturers these days are providing additional features to vehicles, such as remote diagnostics and application-based services. Then we have the local vehicle communications, interfaces such as Bluetooth. Vehicles, especially electric vehicles, have battery charging and management systems. And the people that use transportation, the passengers. They bring their own devices and connect them to transportation and cars. The in-vehicle networks present an attack surface, the computers themselves, and all the sensors that are on modern transportation systems. Telematic units are often added to cars for fleet management and insurance monitoring, and vehicles and transportation will communicate with infrastructure. So we have a huge attack surface that we need to think about when it comes to designing and engineering transportation systems. We also need to understand the failures by human engineering. We know these things happen. They've happened in other systems. The bugs, the backdoors, bad configurations, vulnerabilities that are left within systems, generally poor engineering and complacency. So how do we deal with these issues within transportation cybersecurity? Well, we need to fight back. And we're already doing it. Cybersecurity researchers and bug bounty programs already target vehicle manufacturers and transportation industries. BMW subjected their cars to penetration testing to reveal issues that were later fixed. We need to make the best effort to improve security. As Betchelik said, determined intruders will always find a way to compromise their targets. So we can start applying countermeasures. We can improve the cryptography and authentication that's built into the systems that are within transportation. We can harden the protocols. We can think about secure by design, secure coding practices. We can even put sensors, IDSs and IPS systems within our vehicles and look at strengthening and hardening the sensors. We can also start working together. Within the UK, we have the Zenzik organisation, which is driving forward the connected and automated mobility industry within the UK. The CAM industry has goals. It's there to try and reduce the amount of injury to pedestrians and road users. It wants to improve UK productivity by reducing congestion and give access to transportation to disadvantaged groups. And the UK see new transportation systems and new transportation technology as a growth opportunity economically. Zenzik organises over 100 UK organisations to drive forward technology within the transportation sector. And WMG is a member of Zenzik. Zenzik coordinates the CAM testbed. This is a multi-location facility within the UK that covers all forms of CAM testing. Connected and autonomous vehicles can be tested at several locations within the UK. One of those locations is the Midlands Future Mobility Testbed, within the heart of the UK motor engineering and motor production industry. Midlands Future Mobility is part of CAM Testbed UK. It has 200 plus miles of real world road to allow companies and organisations to test CAM and CAV solutions. And it includes the University of Warwick campus. Zenzik has several what they call golden threads that they use to drive forward innovation within the UK transportation market. These golden threads are part of a roadmap that Zenzik managed to drive forward or innovation within UK CAM technology. And one of those threads is cyber resilience. We need to make sure that our future transportation system are cyber resilient. How do we do that? The UK is also very active within the CAV standards space. The British Standards Institute has its own CAV standards program. We've produced many standards that are available worldwide for countries and organizations to help drive forward their own transportation programs. Standards are part of a triangle, and a triangle to ensure that us, the road users, transportation users, can safely use and benefit from modern transportation systems. This triangle has the regulators who produce the standards on one corner. On the other corner there is us, the customers, who use the vehicles. And then finally we have the manufacturers, who now need to satisfy both the regulators and the customers with the vehicles they produce. What these standards ultimately say is that a vehicle must maintain safe operational use when it is threatened by cyber attacks. The system is designed to be resilient to attacks and respond appropriately when its defenses or sensors fail. Attacks against vehicle systems must maintain safety integrity. We need to avoid vehicles harming the users and the passengers. And now, cybersecurity regulations for vehicles are global. The World Forum for Harmonization of Vehicle Regulations, which sits within the United Nations Economic Commission for Europe, in June 2020 issued vehicle regulations on cybersecurity management systems and vehicle software updates. The UNECE has 64 participating countries within the vehicle regulations group. So it has a global impact on the safety of vehicles. ISO has also released a global standard on road vehicle cybersecurity engineering. The 21434 standard is a multinational effort to develop a cybersecurity process to apply to a vehicle's life cycle. And it should be published later this year. What do these global standards cover? Well, they cover the entire life cycle of a vehicle, from its development to its production, to its destruction at the end of its life. It covers the organization's cybersecurity management processes, how they manage risk, how they identify the risks to a vehicle and assess them and treat them. The security testing processes are also covered under these standards, and the ongoing risk assessments. These standards want manufacturers to monitor, detect, and respond to cyber threats and manage any vulnerabilities that emerge. It covers not only the vehicle, but also any aftermarket services that a manufacturer may wish to market to the customers. And it also considers when vehicles are modified due to software updates. Both the UNECE CSMS regulations and the ISO 21434 standard essentially give the industry a bedrock on which to base their cybersecurity engineering processes. And what are the key messages from these standards? Cybersecurity is organization-wide responsibility. The standards also apply not only to the manufacturers, but also to their suppliers. Threat analysis and risk assessments should be performed. Systems should be secure by design and tested for resilience. Cybersecurity applies to the whole vehicle lifecycle. So a cybersecurity process is required for vehicle engineering. So that was about how standards have been developed for cybersecurity engineering. I now want to briefly talk about a couple of projects within WMG, because we are looking at how to engineer cyber resilience into products. So one of the projects we looked at was the design and delivery of self-driving pods. This was a consortium of organizations that developed and delivered a self-driving vehicle for last mile urban transportation. It was built by Westfield, a UK sports car manufacturer. What WMG looked at was the sensor systems around the vehicle, how they can be attacked. And we were able to use simulation to model the sensors and look at how a vehicle reacts when sensor signals are spoofed. Another example of a project that we did, we were looking at GNSS and the security of the global navigation satellite system. The project highlighted the importance that OEMs need to take when it comes to testing systems and consider potential attacks against the system and any mitigation engineering that needs to take place. Another example of a project, WMG worked with a partner organization that was able to add encryption to the in-vehicle networks and also to the communications from the vehicle to the roadside infrastructure. This project was an example of using real-time cryptographic protocols to secure communications within the vehicle, vastly reducing the threat to spoofing of data messages. What are we learning from our vehicle cybersecurity research? Well, engineers need to consider the misuse cases when they're designing their systems and mitigate the possible threats. We also believe that engineers should try and choose simplicity over complexity when they're designing their systems. The simpler system, the easier it is to test. Design security testing early in the design cycle. We're aiming for a secure by design approach. We need to reduce risks very early in a project. There are also new and emerging design and testing techniques. Engineers need to keep up to date with these trends. Also, hacking modern vehicles is difficult, but engineers can't be complacent. Determination by threat actors will eventually see weaknesses being revealed. So my final points to take away from this. Modern transportation systems provide a very large attack surface. We have already motivations and methodologies for attacking vehicles, but more will emerge. We need to keep understanding these threats to improve safety and security. We need to make future attacks uneconomical by engineering in cyber resilience. We also need to collaborate to share cybersecurity knowledge. And as the UK does within Zenzik, within the CAM community, we need to work as a team to move forward the technology. But there's also an opportunity here. Transportation and vehicle cybersecurity is a very large growth area. Opportunities exist for businesses to flourish in the modern transportation space. So that's my talk on cybersecurity engineering within UK transportation. I hope you found it useful. Thank you.